Hello, gentle readers. It's November 4th, 2025. Today in Reading Foundations, there'll be again, some more of this unscripted sort of reading of these collections from the library of Ross Finlayson, myself, since it's considered supplemental in a sort, an enrichment as it may be, and to reflect on reading and the joy of reading and the learning of reading and these kinds of things, as it's considered something that is a paramount sort of exercise that leads to the ability of people to absorb information and comprehend information, reading comprehension, to where otherwise it's so that almost all endeavors of the modern age involving mental reasoning and the complicated and the code and these kinds of things are difficult, and so it's a great enabler of productivity and in the personal, besides as the of the productivity of the economical in transactional settings. So reading is fundamental. Is one of these things that used to be said when it was sort of being advertised that the educational system needed to provide this to all such aspirants to the prosperous middle class, that the backbone of the middle class is in large part courtesy, this kind of thing, and it's been so for hundreds and hundreds of years since literacy became to be a thing, and among many cultures with success, it's part of the culture to encourage literacy, and so reading is unfortunately having lost sort of its focus among the academic subjects, or as the goals of education itself are proper, instead of just kind of warehousing people to make it so. The idea that according to the needs of their independence, that reading is a key thing. And reading isn't easy for everybody, and that's tough, because it's still something that hopefully, that given the experiences and the time and the inclination and these kinds of things, that it would be accessible to everybody. So that's just something where then it goes that according to that, one of the greatest ideas of learning is imitation, is to show that pretty much all professional people at least are functionally literate, and more so have it open their mind with their entry into the world of books. So that's, I guess, what I'll say about reading then itself today, and then just get into some of these books and so on. So in last episode, which is kind of considered to be about the suspension of disbelief and the suspension of belief, and those kind of always being kind of complementary, and for visual and graphical learners to help show and explore that the big difference is functional literacy, then that you can still be a visual and a graphical learner of both. Then this is kind of this Cosmic Horizons is a book in astronomy, and it helps to relate something that about the understanding of the universe, which anybody can see in the sky, although these days, unfortunately, due to light pollution and the pollution of the orbits, it's hard to see the actual background of the stars in the sky. That something like this book can still help to go to explain all the theory that's behind it, and then thusly that when people are trying to balance their understandings of the world with how one might say the potentials of the world, that it's again something that is for science goes would be inaccessible, except that somehow it's been relayed in this sort of accounts. And one could say, well, you could just show a video of an artist's depiction, a rendition of what this kind of thing would be. But that would just be kind of as of a lens, and according to a deconstructive account, we can disfigure that as sort of not really representative, except as whatever would be as of really passive sort of experience. Whereas reading it necessarily sort of entails that people have to pick up the pieces and put them in their own mental picture, in their own object model of the world. And so I imagine it is thusly very, very well established to anybody who would actually watch these kinds of video essays would know that that is so. They have this at the beginning. They have this spiral, and it says infinity, and it's just the word infinity in a spiral into infinity, or out to infinity. So when looking at a spiral, you can consider it as kind of as a matter of projection. So hopefully in art, everyone's learned the matters of perspective and projection, and the point of a projection and projective infinity, and the point at infinity, and this can look at as kind of like two different things. And one is as a decreasing thing towards a central dot, but another is that it's as descending or going away thing that is all the same size. That because this is rendered on a two-dimensional page, it can be considered two-dimensional and then as an origin, or it can be considered three-dimensional and then perspective on it. So this is just another example of that matters of perspective and projection for grammar and parsing have that the relations that make a space of these words. And so here that was related to sort of something like Quine's language geometry, but it's really kind of just about language geometry. And the idea is that when there's parsing of terms, that there's this whole space of words and this whole space of geometry. And so geometrization is a great way to be able to assign any kind of sort of thing with regards to usual physics and motion and all these kinds of things to a model of as according a geometry. So then the idea that then this language's space of words also has ways to relate that, and then all the comings and goings of those, because these reflect any sort of reflection on terms, not as like the giant ontology of all the knowledge base of all the knowledge inference formats or relational tuples, great ontology, but just whatever is under consideration, left-hand side, right-hand side. So that's then getting into more about the ideas of grammar that here has seen somewhat of a study. And it's related to, or often I find it easiest to employ the latest, greatest artificial intelligence reasoning agent to pull apart what is actually the mechanical act of parsing in a reading. And so it's generally considered as a multi-pass parser, and it's a holistic sort of thing. And it always involves there being a context already, the body of definition, and the dictionary, that if there's one thing that's necessary to make reading possible is to have a ready vocabulary and thusly a lexicon and the spelling. So reading is fundamental, but the only way to make reading possible is spelling drill. That is eventually has it so that that's the only way to introduce words into the context to help distinguish and differentiate them. So that's again another thing that kind of is been going by the wayside, it seems, with regards to the means of instruction, or even just the availability of instructional material for those who'd volunteer their own efforts. It's kind of like for the spelling bee, that everybody should get a copy of all the words in the spelling bee, and then that it's a closed book. The idea that is the test of that is to get it so that everybody has the the ability to enrich themselves with this kind of thing. Expanding our vision. The questions about cosmology. It considers cosmology, this book. The study of the cosmos and our role in the cosmos as the microcosm, whereas it says the macrocosm, where, of course, after spelling it, there's etymology in the parts of speech, the parts of words, to know that micro and macro are so simply as of the greater and the lesser, and to put those words together. The etymology is one of the first words that people should learn. That's 4 syllables, and that it as well is just of its stems and the meaning of the stems of the words that mean stems, etymology, and showing that it's the part and parcel that it doesn't need a Descartes to show that it can be elementarily broken down and made into a thing, but it is so that everybody should at least have a chance to see that there's quite a structure in these things, and it then results in the natural language. So this is something to get figured out some more, I suppose. The idea is presented. There's a representation principle, and the idea is that what we see is real, and so that's relevant because there's things so far away that it's diminished to nothing what we can see, and so it could be whether the moon is made of green cheese or whether the moon has moons and valleys. So this was known hundreds and thousands of years before Galileo figured out a 3 times telescope and pointed it at the moon and started to argue that the moon was not a spherical orb, but instead had moons and ridges and valleys. And so this is kind of the idea then that there is representation. And then we have our theory of science, of course. And here the idea is like, well, yeah, theory of science is great, but you kind of have to have truth first. And then you can, the whole point of science is to establish that science has its limits and its strengths about truth, and including about truth in the theory. So yeah, that can be considered from some of the other talks here a little bit more thoroughly, which usually are just very much commonsensical. I mean, a true theory, of course, is very much commonsensical. And then getting about the paradoxes of mathematical logic and this kind of thing, trying to figure out what those would be and then how to resolve them. And it's here's, for example, he says, Heraclides of Pontus, Aristotle's contemporary, was apparently the first to assert that the Earth rotates, thus explaining why the stars and other celestial objects appear to move across the sky. A rotating Earth, however, seems less likely to be the center of the cosmos than a fixed Earth. So this gets into the examples of that. This was very well known before the times of, Copernicus, thousands of years later. And so it helps sometimes that, yeah, they kind of had a pretty good idea back before 2,000 years ago that the Earth was spherical and approximately its radius and these kinds of things, vis-a-vis the ideas of like going from California to Hawaii or something like that. It's like, oh, it's kind of around the bend, and trying to figure out these kinds of things. The Copernican revolution, Copernicus, and this is kind of discussing that one about the epicycles, because before it's like, well, everything's just spherical and we're in the center of the concentric celestial spheres. It's like, okay, well, now we're not the center of the universe anymore. It's like, well, it's or that's elliptical, and the planets and their interactions. Well, then there's epicycles. It's not spherical. There's just loops now added. It's like, okay, and then we get way forward to Kepler, and he's like, the ellipse is the pretty much simplest thing, because the ellipsis is as of where the ellipsis is just ... but the ellipsis as of the least difference in potential according to the inverse square law. So then before that, Newton came up with a system of the world, and he's like, well, look, my theorem of gravity according to inverse square law, and me integrating it according to this calculus makes it so that I've perfectly drawn a diagram, and all the planets happen to follow it almost precisely. It's like, well, that's great. I mean, it's really to be considered that for Kepler, after Bode's law, that was a great idea, and it pretty much exactly matches Bode's law and Kepler's law, and that's fantastic. Tycho Brahe. So this is just getting into kind of the modern approach. Kepler and the orbits of the planets. Kepler, Copernicus, Kepler. The Harmonices Mundi, that's been looked at or read here before. It'll perhaps come up again as I kind of go through the libraries as I'm getting prepared to put them on the shelves somewhere. Harmonies of the World, in which he announced his third law of planetary motion. The law states the relationship between the time a planet takes to complete one orbit about the sun, its orbital period, and its average distance from the sun. The orbital period of a planet is proportional to the cube of the square root, the 3/2 power of its average distance from the sun. Galileo and Newton, and here it's considered there's like Newton's zeroth laws besides, and there's Aristotle and then no unmoved mover, yet there is then for worlds turn. These kind of ideas, it's because circular movement is eternal, and then for acceleration and the whole account after moment of motion of the real of the models of state in motion, moment in motion, the geometry is motion and perspective and projection. He's talking about Haley and Jean-Philippe de Josot suggests that matter between the stars and interstellar space absorbs starlight, thus explaining how an infinite universe might not necessarily produce a night sky as radiant as the sun. This is related to the Olbers paradox, which is like, well, how could it be that there's stars everywhere, it's full of stars, and the night sky is more a coal sack. It's not full of stars. And it's like, well, it's just interstellar dust is the idea. So these are the theories of stellar pulsation. And they're established furthermore by the models of hydrogen spectroscopy. And it's like, well, we can actually see some light through this. And so then we have these models of stellar formation and pulsation, which is like, well, according to a given size and a given configuration and a given estimated density of these elements, from what we can see and survey according to spectroscopy, then you can sort of say that when we look out of the sky and we see all these stars of a given particular temperature, then it's figured that they're all of a given same sort of size and they're the same sort of composition. And so when they're of various brightness, then just you can figure that they're the same sort of distance. That's the only measuring stick really that there is or was for optical astronomy, was this idea of the standard candle, a star of a particularly well-known or presumably well-known composition, and according to theories of stellar formation and pulsation, that would serve as an idea of how far things are in the sky merely by the intensity of the light. So that's the kind of the fundamental establishment of astronomy. And then these days for the radio wave astronomy and the gravitational wave astronomy has that there's a Newtonian theory of gravity. And here, for example, it was just discussed a little bit last time. It was like, well, Einstein's theory has always been confirmed, right? It's like, well, yeah, but there's 13 different ways to confirm it, so they often don't say which way it was. And so then there's anything else that's not so confirmed. It's like, well, so nothing's been unconfirmed about Einstein, right? It's like, well, I don't know about that because dark matter and dark energy throw essentially the entire thing out the window. And the same kind of goes for Newtonian gravity. But then as for Newtonian gravity, it's like, well, everything around the Earth is about the curvature of space-time, right? It's like, yeah, I suppose you could say that, but it's just called parameterized post-Newtonian. That's the formalism that everything according to the Jet Propulsion Laboratory in the sky around the Earth flies according to the way it does, according to gravity. So as gravity's speed is limited by the speed of light, right? We know that according to relativity theory, according to the L principle, L being a constant, the speed of light, according to mass energy equivalency, that any mass approaching the speed of light would take infinitely much energy to get it to the speed of light, so that nothing can go faster than the speed of light. So information can't go faster than the speed of light, according to this relativity theory. And then thusly, the gravitational wave observatory is so limited by the speed of light, and all we know is that nothing can go faster than the speed of light, which is a finite constant, and so gravity's speed can't be any bigger. It's like, well, no, not really, because if you actually like look out in the sky at the planets and their orbits, as according to Kepler and Newton and all the sky survey, the only way that it works, that the force is always pulling in the right direction, so they stay in their observed orbits, is that the pictures we see, which are kind of behind where they are, like with the moon being a few light seconds away and the sun being a light minute away, or a few more, or one astronomical unit, has that. The geodesy always follows the sources as where they really are, not the image. So you can't really say that the gravity speed is any less than light speed, and you really can't say that light speed is as fast as gravity's speed, reflecting that the current solar system is like so, because the solar system would fly apart unless the geodesy is everywhere evaluated as instantaneously. So I suppose that's one of the problems with the instruction of relativity theory, is the consequences of mass energy equivalency and the Ella principle put together make it so that then that's not to be that's about accelerating something that's still kind of in the classical, but gravity's speed then, because that's now gotten into like, well, no information can go faster than the speed of light. There's no instantaneous information. Furthermore, then that breaks for curved space-time all such matters of the relativity of simultaneity. So we've read from Einstein here about out of his later years, he helps clarify, he's like, hey, that's special relativities, and we got the spatial, and then we got the spatial, and these are two different things, because the relativity of simultaneity is non-local. And so it's really tough to try and take a look at what would otherwise be this kind of closed Newton's system of the world, because that does not have relativistic dynamics in it, which are displayed by things like mass energy equivalency and space contraction, length contraction, and time dilation put together. That there's all these different matters of ways that people can solve the Lorentzians for Fresnel, Fatio, Faraday, Fizeau, one might say, Finlay-Freundlich and FitzGerald. So kind of for the E energy of Einstein, all these fields and forces, these other F names. Fatio for gravity and a fall gravity after a pull gravity instead of or push gravity instead of a pull gravity. And Fresnel about all things light, because Fresnel is just considered the greatest optician, and to go along with Huygens, who is yet more of a reductionist in that field. And then see, Fatio, Fresnel, FitzGerald is about with Heaviside being these are the classic real fields of the electrical and for what it means for the electrical constants of light about light speed, as O.W. Richardson puts in this book right here, The Electron Theory of Matter, that there are three different constants C that are different, and one's slightly greater than light speed and one's slightly less. And they're all said to be the same because that's kind of where they line up or point together at their point in infinity with regards to each other. So then there's something like Fatio, Fresnel, FitzGerald. There's Finlay-Freundlich. So Finlay-Freundlich was a colleague of Albert Einstein, and who he would have he tried along with Eddington to be the first to find the pictures of Mercury peeking around the edge of the sun to show that the light's bending would show the curvature of space-time, or at least light following the geodesy or following its orbifold. That then as well. Finlay-Freundlich or Erwin-Freundlich wrote a great paper on gravitation for general relativity that you can find in places like what's the word, the open press guy, or the guy who invented the printing press is what it's named. So there's a project named for the guy who invented the printing press, and it'll come to my mind in a brief moment. That after it's been 100 years, that Freundlich's later works are there. So that's reflecting on largely Einstein's kind of view of things. And then these other sorts of approaches for these different fields then make for ways to help understand that light speed is a constant in deep space, and around here, meaning around the Earth, and then as with regards to variously, around the Sun, it's measured to be so in terms of astronomical units, as has been looked at here in some of these other works in previous talks, that this is the kind of thing that helps to go to show that then after the optical astronomy, which is like we're sitting in the center and we have these candles around, and by their intensity we can tell their distance, to radio astronomy, which is variously from like punching holes one way or another, gamma rays, to just radio waves, and the high and low frequency of radio waves about the optical spectrum. And the optical light is special, and the nuclear radiation is kind of the same. And then as for something like that, the electrical, the radio waves, those are kind of the high and low aspects of it with regards to the frequency of radio waves. That's the thing, and slightly underexplored, but classical right down the middle. Otherwise, it's a very careful balance of considerations that was arrived at by already kind of having funneled everything into where that's the only thing that makes sense. That it's just goes to show that according to the Sky Survey, the solar system does not fly apart, and dark matter and dark energy have definitely invalidated these more naive theories, including about gravity, whether Newtonian or Einsteinian. And so then it's got to be kind of like a fall gravity. So Fatio and LeSage is kind of the idea there for that. So yeah, Fatio, Fresnel, Fizeau is for light speed as a constant, and these kinds of things. FitzGerald, Finlay-Freundlich. There's some more of these to talk about the fields and the forces with regards otherwise to Einstein and energy, as it might be kind of put. So that's one way to help establish that, and that's the things going on. Here it shows that there are galaxies that are spirals and there are galaxies that are clusters. William Parsons, later the Earl of Rosse, used what was in the 1840s the world's largest telescope to draw the appearance of the Whirlpool Nebula. Today we know this nebula to be a giant spiral galaxy. Evolution of thought and evolution of the universe. Slipho and Hubble. Hubble is held up as a great guy. So then though revisiting Hubble, Heisenberg, and Higgs is that, well, Hubble, redshift ain't a thing. And so now we got to look at all the stuff that went into that, which made for Lemaitre, and it's like Big Bang Theory is perfect. It works and it fits. It's like, well, yeah, but now it doesn't, And then envision Heisenberg is with regards to determinacy and indeterminacy. It's like, so what's wave? It's particle. It's determinate. It's indeterminate. It's observable. It's not observable. It's like, well, yeah, but how about some Heisenberg determinacy if it's going to have to be that way? And then that's what you need to attain to. It's like the Machian principle applied to that. And then Higgs is kind of like, well, we've unified at least one corner of the electrical force and this the strong nuclear force a little bit. And we're going to say that it's now we've made a Higgs boson. And it's like, well, that's great, Higgs, but your field isn't a classical field. Your particle is not a standard particle. It's a doublet. It's two particles. So this is the usual idea to revisit Hubble, Heisenberg, and Higgs is helping. Otherwise, to have to explain it's like, we can't possibly agree with the science that we had, but the science that we have is telling us nothing. These kinds of things that, these are the kinds of things. With regards to the theory, this is physics, I guess, today. The types of elementary particles, leptons, quarks, and bosons. So the force carriers is generally the idea is like, well, in a theory is like, well, nothing moves. Okay, now it moves just the least amount. Okay, now it moves the least amount and like the least distant. It's like, well, what moves? Like, well, the force carrier moves. So it's like it's an electron, or it's a a neutron or proton or whatever it is according to master charge. And then for time, it's like, well, what's time is like? Well, it's time itself. And then for how about this nuclear theory or something like that? Well, it's like, well, it's just sitting there. It's kind of like not time stopped itself. That these are the force carriers. Reflects on that quarks were by Murray Gell-Mann, who along with George Zweig first proposed their existence, chose the name quarks because 3 quarks are needed, as from James Joyce in Finnegan's Wake. So quarks for Mr. Mark. What those are in Finnegan's Wake, I would have to kind of reestablish it. But I imagine it might be alcohol. I'm not quite sure. But I think it means like pips, like to 3 salvos, say. The boson theory. Gravitational electromagnetic radiation represent large numbers of free gravitons and photons, respectively, streaming through space at the speed of light. So gravitons. See, this is where what's graviton supposed to be, and it's like, well, graviton is kind of like the virtual particle or the force carrier of this idea. What gravity is supposed to be, the quantum gravity. Well, what can it be? It's like, well, it's got to be huge. Well, it's got to be small and tiny. Well, how about it's just exactly the same as the atom? It's like, well, the atom's classical. It can't move. It can't be anything according to Born rule and Pauli principle. Anything at all that's tried to be relayed here is like moving the pieces, the field of gravity. It's like, yeah, it's kind of tough to figure out these days because in the ancient times, the only theory of gravity is like what goes up must come down. There's gravity. We all know that's this thing. Let me prove it to you. And like throw a rock in the air or something. But today it's like, well, what's the theory of gravity and where is it? It's like, well, it can't exist with our theories because it would violate the conservation of energy everywhere, all at once, everywhere. So in relativity, it would be so that, well, it has to be Newtonian. And what does that? Is like, well, that would be perpetual motion. It would be constantly doing work for free forever. According to that, we can't find anywhere else that's just flowing back the other way. It's like, well, okay, how about quantum mechanics? It's like, well, we got classical orbitals, it's all by charge. And then at the same time, the gravity holds things together pretty clearly and obviously. The strong nuclear force would be kind of that way. It's if you treated them, all the subatomic particles with mass like tiny gravitational singularities. It's like, okay, great. So that works. Is that gravity? Well, no, because then everything in the whole universe would be in a black hole and instantly all at once, and it would just be one little dot. So something's got to like hold that up, and so that would violate conservation energy. So between quantum mechanics and general relativity, is there gravity kind of in the middle? It's like, well, yeah, it's kind of all around. So making the fall gravity is the idea of what it is instead of Newton's kind of pull gravity. And that like the Earth pulls us down, and that's the way it is. And so the planets just kind of hold themselves together, and it's like, which is a great model, and it's classical, and it is so according to the same thing. And then Fatio and LeSage were like, well, instead of that, because they by now noticed that this would violate these otherwise principles of the theory being inconsistent at all, said, well, things just kind of, there's something on the outside of the universe that pushes everything together. And so this is then was like, well, then they'd have to be infinitely fast, and they'd have to, be infinitely small, and that these particles making a stream of particles, and so then the idea of a fall gravity is just kind of like that. But what they discovered in the nuclear force and the strong nuclear force that holds atoms together is the idea, and that's some of which is liberated in nuclear fission. Then the idea is that, well, in the center of that, there's these quarks are held together. In the very, very center, not at all. It's asymptotic freedom. This is Solomon Weinberg and Gross and Wilczek and these guys who got a Nobel Prize back in the 70s about making one of the greatest kinds of accounts. So then, so a fall gravity could actually just be the same thing as the nuclear force existing at all, and then it would solve all these problems, except we just have one mathematical problem about how it's so from outside the rest of the universe to make it so. It's like, yeah. So and then that would just be like infinitely fast, the speed of gravity. Well, yeah, that would kind of have to be so. It's like, well, wouldn't that violate relativity and all our theories, or otherwise it's all the physics and the conservation and the least action and the and those things. It's like, well, no, but you just need infinity in your mathematics first, without that being a paradox. Oh, that's so simple then. Oh, great, great. So the theory of cosmology is kind of advised by when they're looking at stuff like the Weber bars and gravitational wave detectors and these kinds of things, which have been around for a while. And even the idea of the thought experiments is like, well, yeah, you just would need a sufficiently large experiment in space to show that two observers could be arbitrarily far apart as long as they start at the same place and split all apart, and then one in the middle kind of leans either way, and then it would be immediately obvious to both of them for faster than light, the super-luminal, that it's still metered so strongly. I mean, it's not just a matter of, wishing it into existence in a sense, except because information can be arbitrarily small, or images can be arbitrarily dense in a sense with regards to things like resolution. It's just to go to show that for somebody like Mach and the idea that, bees can't fly, meaning once upon a time theory got together and was like, well, bees can't fly. Our theory of wings does not allow them to fly. And these kinds of things. Or like, nobody can sit on a stool and kind of spin themselves around, or these kinds of things. Or like, why does not everything explode when it goes 60 miles per hour? Wouldn't it shake itself apart according to the theory? At some point in time, the theory is like, well, yeah, it does. And then the idea of the speed of sound, that would automatically explode. It can't go faster than the speed of sound because according to just adding up these ripples the other way and just pointing them in a corner as after a partial account, it's like it would just blow up. It's like, how about the speed of light? Well, it's like the speed of light. It's like, no, actually, that's a really good hard value because the acceleration required to get something according to this mass energy equivalence holding up, but that would be like not so. So it's like, well, what about if, and that's in the space, right? Well, yeah, that's in like the space. It's like, when in relativity theory, what's relative? It's like only motion is relative. Everything else is absolute. So then Einstein comes up with a spatial for special relativity and a spatial to keeping that for general relativity. It's like, so nothing can move into space going faster than light speed. No. Okay. So what about if the space goes along with the frame? That the space actually moves, and it basically makes for these ideas of like a Cuvier and the warp. Because, of course, people have always been like, well, that's impossible. I'm going to try and, outdo it. So Alcubierre is usually given an idea of the warp, the space warp drive. Compared to things like the wormhole and like the hyperspaces, the idea is like, well, somehow the whole space folds in, and we can take one tiny step, like an ant on an accordion, and when the accordion opens back up, we're on the next louver of a sort. That then the hyperspace is more the usual notion of like, I'm moving forward, there's things in front of me are oncoming, things behind are receding, these kinds of things. And so space frames and frame spaces kind of make for like, well, everything, according to everything in inertial systems, in these dynamical systems, these differential systems, all of matter in physics, according to this theory, Einstein's relativity, according to Einstein here, has that it's in frames. And so all the things about relativistic dynamics and moving frames and co-moving frames and static frames and the terrestrial frame and the lab frame, all about frames. So it's like, wow, does the space actually go with them? Because maybe then space is relative. It's like, well, yes, space is not relative because all our rigid rods and the metrics and norms is the only thing we have left to add stuff back together. Because at the end of the day, it's like, well, we have to be able to tell in the ephemeris or where in the solar system things are. It's like, where are they going to be there at that time? So putting that back together, it kind of involves taking it back apart a little bit and then putting that both back together, kind of like trying to make a jigsaw puzzle in the air and without it like falling over, But it is possible, and so it just goes to show. Then when they look at the sky today and they see stuff is like that. Dual neutron star is emitting a jet, which according to what we looked at last year is going faster than light. Super-luminal. It's like, well, if you just kind of consider it, it must be somehow at an angle, so we're just like at the wrong angle. Our optics can't be correct, or something like that. It's like, so it's an illusion, because otherwise it would just violate the theory. And it's like, well, when you look at it, the dark matter has already made it so that like this galaxy shouldn't even be holding itself together, but it doesn't have any matter to explain according to the way things are. That's like so that here that's just like worlds turn, and it's got a free rotating frame, because then space contraction gets involved, space contraction linear and space contractional rotational. These are simply the parts just sitting around that could otherwise keep it from destroying itself. Because anybody can use an automated theorem prover to just pick up these facts and just say, oh, I've invalidated the theory. I've invalidated the entire theory of physics today. And so that doesn't help much when it's like, you can't put it back together while you're at it, Thusly, what we're arriving at here is for that, by understanding a little bit more about the space frames and frame spaces, then for space contraction linear and space contraction rotational, that the linear and rotational are different with regards to kinetics and kinematics, and then for the world's turn bit, and then the hypercube distance, and some of these other ideas about the Zolfray metric or something like that, or with geometry and all these kinds of things, and not stuff necessarily that I say about it, of course, except that frame spaces and space frames are kind of like, I just say those are the words that fit, it must, and these kinds of things. And the space contraction linear and space contraction rotational, it's like, well, yeah, Heaviside or FitzGerald already put that back together before it even became a thing called the relativity theory, space contraction, and so the time dilation and length contraction being two different things is like, they're never two different things, they always go together. Besides that, in some particular models of, well, if we look at only light and only theory, this is the only thing in the theory, then it would be one of two things. It's always one thing. Helps go to show that the account then can make for why there's it's kind of so simply to be arrived at then otherwise, that without getting kind of, as mentioned last time, in the whole tower of a grand modern program for mathematics and all its formalisms and the derivations to arrive at the stack at the top, which is broken, then this is kind of the same thing goes for physics. And so that this way, but there's still like this usual notion of a tetrad of quantities: earth, air, fire, and water, the classic four elements, neutrons, protons, electrons, photons, the classic four subatomic particles. These kinds of things. The nuclear force, the electrical force, the weak and the electroweak forces, these kinds of things. Then without having to add a fifth one, it's like, well, gravity is the nuclear force just all the way out to the edge of the universe. Helps to go to show that these ideas then for a tetrad of quantities in forces or fields or particles or elements is pretty thorough and sufficient. And for things like three space dimensions and array of time, why these are pretty usual sorts of ideas here. So foundations, I guess if it was a little bit about reading to begin, but it's been about foundations then ongoing. So let's then try to clear out the rest of this box so briefly. We'll just see what's in the box. Let's now examine some of the characteristics of the four fundamental forces that govern the cosmos. 1, gravitation; 2, electromagnetism; 3, weak; and 4, strong. So it's a similar kind of thing. Neutrinos, and they're like the electron physics, the muon physics, the neutrino physics, and the hadron physics. For the classical and 3 kinds of supersymmetry. Augmented plane wave method, Terry Lukes, Loucks. Augmented plane wave method. So kind of like Euler and Gauss, and making for an arithmetic and a periodic and the modular, and Wick rotation, which is used in quantum mechanics to like make a line integral or this kind of thing. And similarly for lots of different things, this is just kind of like a plane wave is like its periodic potential, except for an occasion encounter with the surface. The itinerant electrons in a perfect single crystal have a fairly boring experience. The electronic potential energy is quite repetitious. This periodicity can be expressed by this vector of, or this potential v for potential often enough, of these two vectors, right, r plus L equals VR, where L equals L1A1 plus L2A2 plus L3A3. The vector L specifies the positions of each of the unit cells in the crystal. So this is helping to go show that electrons, as their oscillations would be, or electron holes, it's usually put these days, vis-a-vis electron beams and scattering. It's like, well, current is not that involved, and it also doesn't have diffraction. It's just electrical current. So those are just the electron holes moving along, as otherwise kind of like electrons move forward and they move back, so they leave a vacuum or void, and then so the next electron to his neighbor fills that void and moves back. So the hole that is left by it is the current moving along, electron holes. That's the usual course given for Leonard Weichert in how electricity works. Then this author is helping explain that there's this augmented plane wave method to make another way to look at that. For example, it would be a similar kind of way. But then, of course, he's got all these different numbers and experiments showing us also that is so according to all these measurements. Glenn A. Burdick, energy band structure of copper, energy bands for solid, AR, LF Matisse. So all these papers in this, band structure and magnetism of gadolinium metal by Dimmock and Freeman. This is from 1964. So all this stuff is part of material science, I guess you'd call it. That it has in it an introduction about the APW method and these reprints. So it's got a bunch of reprints in it after developing method. So the first 150 pages are like this plane wave method. Then he's got all these reprints that perhaps he considered to apply it to. And these would be usually probably considered important. Slater and Wood and Burdick and Conklin, Pratt, Johnson on the relativistic effects in the band structure of lead tellurium. Energy bands for solid argon by Matisse, and the Fermi surface of beryllium by Terrell. When you see Terrell in a physics, that's heavy. Terrell is considered good, kind of like Fritz London. Terrell is kind of mythical in a sense. L.F. Matisse and Ari Watson, Dimmock and Freeman, Sweitendick, Ern and Sweitendick, Lukes, and so this relativistic energy bands for tungsten by Lukes is this reprint, is kind of added to it. So this is from 1965, but these early papers start with J.C. Slater in 37 and J.H. Wood in 62, and then 62 through 65. It should be emphasized that lecture notes are necessarily rough and informal, both in style and content, and those in this series will prove no exception. This is as it should be. The point of this series is to offer new, rapid, more informal, and in its hope more effective ways for physicists to teach one another. The point is lost if only elegant notes qualify. Well, I don't know about that, because you can just read that off as notes. Okay, what's left in the box? Elementary Particles by I.S. Hughes, 2nd edition. As you can imagine, this book from Cambridge Press is about particle physics and elementary particles. It's from 1972. To his wife, or one of them. Accelerators, beams, and detectors. Particle detectors, particle accelerators, and beams. Now, there's a lot of different experiments that could go on. Pions and muons, conservation laws, strong, weak, and electromagnetic interactions, strange particles. These are called exotic particles, usually. Spin and parity of the K mesons and non-conservation of parity and weak interactions. So this is mesons and the muons and muon decay and beta decay. Or here it's tau decay. Weak interactions in this neutron beta decay. And so this is like the electron, the muon, the neutrino, and the hadron physics. Invariance under the charge parity and time operations, properties of K mesons, the theorem of the invariances, and the usual idea that time invariance is the only one that's never been falsified with regards to things like antimatter and magnetic monopoles, strongly decaying resonances, SU3 in the quark model. There's eventually, it's like, well, remember when we were talking about like that gravity is from the infinite edge of the universe, and so we don't have mathematics infinity yet, but we need that because that's what it is. It's like, yeah, it's like, well, how about the special unitary group in order 3? So it's kind of like the 3 space dimensions. Like, yeah, what about it? Everything rotates around that. It's like, well, it's kind of like that to infinity, but then it has to fit back in 3 too. So it's kind of hollow dimensional in a sense. So you're like SU to the n, the natural numbers, yeah. Weak interactions and weak electromagnetic unification. New flavors, quark and gluon interactions. Quarks are particles, and then they're held together by gluons, is the idea. So it's like, well, so the atom's made up of quarks. Well, quarks and gluons, you know. It's like, why are those there? It's because, well, otherwise they wouldn't be there. Higher symmetries, relativistic kinematics in phase space is in appendix. Klebsch-Gordon coefficients and particle properties. Probably after all that is like, this is a way to scratch a line on it so you can say that you can put it in the paper. You know, appendix B. Gell-Mann-Nishijima scheme. So this has got all sorts of geometry, algebra. It's all geometric, but algebra, and some trigonometric identities, the ideas of what spin and the ideas of these properties of these particles have with regards to these algebraic groups. So this is a nice account. I mean, here it's considered a little bit more from like the older works that this is based on. Well, at the same time, something like, you know, and here's our latest greatest method to, you know, get a paper published. Magnetic research and magnetic resonance and biological research. So this is pretty heavy-duty stuff here. Caffiero-Franconi, Laboratory of Molecular Spectroscopy, published by Gordon and Breach. University of Cagliari, and if I pronounce that incorrectly, it's not intended to be incorrect. The growing need for an up-to-date survey of research into complex biological systems by magnetic resonance techniques is answered in this important new reference work. So this is considered in the book about medical imaging. That's like a modern textbook explaining a lot of sorts of approaches and techniques with regards to, but magnetic resonance in particular for MRI and nuclear magnetic resonance and magnetic resonance imaging helps go to show that it's like, well, yeah, this is kind of a field altogether of these things that is not the same as just X-rays or and these kinds of things. Because by the time they got enough X-rays pointed out to make enough slices for computer tomography, that would be the end. That would have caused too much damage. But then this nuclear magnetic resonating and magnetic resonance and resonance imaging, it's kind of like, well, this can happen, and it's not to be regular, but so far it's like it's at least your worries at that point, kind of thing. And this is something I just need to study some more with regards to this conformational changes in proteins. And this is the computed parameters for the transfer of aliphatic alcohols from a hydrocarbon solvent into water are compared in Table 2 with the experimental values compiled from several sources in recent publications. Just an example. And you talk about the errors. Presumably due to the small size of the alkyl chain, some of the simple assumptions made in the hydrocarbon theory break down here. The parent theory for hydrocarbons also gave the worst agreement for methane. The present calculations were not extended beyond N-butanol because the treatment of longer alkyl chains requires several modifications of the computations due to the possibility of folding of the alkyl chain. And so the resonances involve stimulating this areas with resonance, nuclear resonance fields, their changes in their interactions. I mean, it's not just like one magnet that's on, it's like constantly vibrating at a very particular thing, and then going forward and back, reciprocating to get an echo, essentially an echo back from where it's pointed at, because it can be kind of triangulated and pointed at these things, where the wave meets in the middle. That it's basically sets up a standing wave, bounces something off that, and then moves that, and continues for computerized tomography. Is my idea. That this book has a bunch of different contributions. As of that, this is magnetic resonances in biological research, 1971. This book contains the reports of physicists, chemists, and biologists working in the field of magnetic resonance spectroscopy upon the systems of biological interests. These reports were read at the Third International Conference on Magnetic Resonances in Biological Research held at S. Margherita of Cagliari, Italy. Among the radio frequency spectroscopies, magnetic resonance spectroscopies play a very important role, chiefly because they involve electron and nuclear spins and their associated magnetic moments. In fact, many spin magnetic interactions are present at molecular level, and the results of their study have been quite rewarding, so that new fields of research are now fully developed regarding studies of structure, conformation, electronic distribution of molecules, molecular and lattice symmetry, and dynamics. Also, molecules of biological interest, together with biological systems, were subject to analysis by magnetic resonance spectroscopies, and many significant data at molecular level of interest to biochemists have already been collected. In fact, in recent years, parallel developments have occurred in the understanding of both molecular biology and spin magnetic interactions, so that today, given also the tremendous improvement of the basic instrumentation, it is possible to describe many biologically important problems in molecular terms, which can be studied by magnetic resonance spectroscopies. Thus, the latter methods of investigation have become a unique tool for taking further steps toward a better definition of major problems, such as the relationships between molecular properties and biological specificity. 1969. Caffiero Franconi. P. Pratesi, in the opening address, says, there are valid reasons for believing that study of the structure of proteins and of their interactions may lead to the formulation of valid hypotheses about the dynamics of the so-called receptors, that is, of those particular receptive chemical structures, the biological substrates that interact with drugs and are believed to be responsible for the specificity of the drugs themselves. Oh, so he's just basically suggesting, it's like, well, it could be possible to affect conformational activity in proteins, or like metabolism, as it's usually called, as kind of via remote, say. Intermolecular forces and conformational changes in protein-ligand interactions, a curve-fitting procedure for the study of the binding of small molecules to multi-subunit proteins. Nuclear magnetic resonance studies on selectivity deuterated staphylococcal nuclease. So this is basically, well, put in some heavy hydrogen, and then that we can it'll wobble and jiggle different. A review of ESR studies, electrospectroscopy must be, studies on hemoglobin and its derivatives, a crystal field analysis of low-spin compounds of hemoglobin, blood, its main compound, a theoretical study of EPR spectra due to high-spin ferric ions in proteins, NMR studies of the role of the heme group during the cooperative oxygenation of hemoglobin, so more study of blood, NMR studies of hemoglobins, EPR and NMR spectra of some hemin derivatives on the nature of hemoglobin is found in Heinz bodies of red cells from patients with alpha thalassemia. There's about 38 papers in this book to consider. So it kind of reminds me of the turbulence theory book. This is like, nuclear atomic turbulence theory. And radar, in kind of a sense. This is like, well, this is some literature. This is a nice Nin's Waste of Timelessness. Another early stories by Ines Nin. Carmen Maria Machado's Her Body and Other Parties. A love letter to an obstinate genre that won't be gentrified. It's a wild thing, this book, covered in sequins and scales. National Book Award finalist. This is from a few years ago. It's all right. This is a pretty good book. Many comments, reviews in the front say, astonishing. Carmen Maria Machado is the way forward. Kevin Brockmeyer. Surely one of the most ferociously gifted young writers working today. I was drawn to it because of the idea of that is some interest. 2017. Let's see, to try to just read these off and then perhaps go back to something that's otherwise. Because there's another box of books to figure out. Okay. Lasers in plastic surgery and dermatology. So, lasers are like knives, kind of. Neurobiology of Periodic Psychoses, edited by Noboru Harotani, MD, and Junichi Nomura, MD. So this is about the structural basis of psychiatry, the diagnosis and treatment of mental disorders, the neurobiology of periodic psychoses. So we'll just leave that first. I want to look at that a little bit. Current topics in biochemistry. So this is just a review in a sense. The National Institutes of Health lectures in biomedical sciences. Academic press. The prices noted for it have varied over the years and tend to go up, or at least stay constant. 1972. So this costs more than it cost. This is explaining some basic functions and the metabolism and the genetic structure so related to the proteins so involved. Appreciation of ancient and medieval science during the Renaissance, 1450 to 1600, by George Sarton. So Sarton is a historian, and he's pretty great. And this is something to read a little bit more thoroughly later because it kind of reflects on the times and the development of the history of the science. Techniques of Polymer Characterization, 1959. So this is lab methods. Is, for example, about the ultracentrifugation and these kinds of things. Geophysical signal analysis. So this is for things like vertical electroresistivity sounding or ground penetrating radar, geophysical signal analysis, or echo sounding and these kinds of things, about how to implement such a device, say. And that's where something like, it's like the Great Satellite Eye in the sky has made a great map of everything in the on the face of the Earth. But what's underneath it? It's like, well, you got to kind of get a little bit closer to find out what's underneath the Earth. Hey, have a great day, gentle readers. Today is pretty much a talk about theory after a little bit of reading, so reading and foundations. But it's kind of like about what goes into the absolute theory of relativity, and it's like about relative space in a sense. But I'll think of a title. Hey, have a great day. Goodbye.